So next Monday and Wednesday, it's a holiday, I think, at LSU, right? So there are no classes. And the week after that, I'm going to be going to Canada to serve on a panel for a whole week. So Mrinal will take the lectures and he will take you through COMSOL implementation of some of the nonlinear algebraic models, continuation methods, and maybe some ordinary differential equations as well. We will see the algorithms for solving these later in the course. But he will set you up so that you know how to use COMSOL so that you can get started in your project. And the project list should be coming to you in about a week's time. Okay. Till this Friday, I'm really tied up to my neck, but hopefully over the weekend I will prepare, Mrinal and I will prepare a set of projects for each one of you to pick, and then you can start working on that. So, any questions for me before I start? Okay, I'm just checking periodically to see if there are any questions. The only way I can see is by flipping to the other screen. So if there are any questions, you can either raise your hand, and there is an icon that you will see on the top, and or put it in the chat box. I'll check that periodically. Okay. Garrett has joined too. Welcome from wherever you are. All right. So in the last lecture, we are still developing these ideas of eigenvalues, eigenvectors, orthogonalization of vectors. And we saw ideas about minimization. When we have a non-square matrix, how do we get the solution in the least square sense? So we formulated by minimizing the objective function as the residual, square of the residual errors. We formulated a normal, what we call a normal equation, an augmented equation, which is nothing but A transpose AX equals A transpose B, which becomes a square matrix, a symmetric matrix, and which you can then solve using the regular LU decomposition or any other iterative methods. Then we started looking at one example of an iterative method. This is a whole class of methods that have been developed, and in a linear algebra course devoted to linear algebra, you will see all the variations of this. But we are going to see the basic ideas involved in the conjugate gradient method, so that when you're using COMSOL, you know what type of, you have a rough idea of what type of algorithms that you are using. And the problem still is the same, that we are solving an equation AX equal to B. Okay. But in an iterative method. So we're going to make a guess for the vector X, which will give you a residual which is not going to be equal to 0. So we will call that AX naught minus B. X naught is your initial guess, which gives rise to an R naught, which is your initial residual, initial error. And any iterative method must drive the error towards 0. Okay? And in the conjugate gradient method, it is, we can show, and I think we did in the last class, it is equivalent to minimizing this objective function. So if you take the derivative of this function with respect to x and set that equal to 0, you will recover the equation AX equal to B. Okay, that implies that if you minimize this function, you are going to satisfy that condition, that you're going to solve the particular equation. And the way that we do that is by making an initial guess vector, calculating the residual. Knowing the direction of the residual, we are going to pick a search direction. Initially, it may be the residual direction. And then in the search direction, we need to decide how far we want to go. And once you go to that particular end of that vector, we want to find a new search direction that will be orthogonal to the original search direction, or it will be in the steepest gradient, the steepest descent direction at every point. So if you do that, you will find that in a few iterations, you can get to the minimum, and the minimum will be the solution to that particular problem. That's the basic idea. Okay, so at any iteration level, then we are going to say that the residual is given by the difference between B and AXK, the guess vector at the kth level. Okay, and so as I said earlier, once you go in that direction a certain distance, you want to find the next search direction. Okay, and this is the equation that is going to give you what the next search direction is. And what is the meaning for this? Okay, so Rk is the current residual that you see here, and how can you interpret this term in relation to the Gram-Schmidt procedure that we have seen? If you have a vector, if you want to subtract all the known components from the vector, we just subtract it. That's what we do, right? So Pi, I going from 1 to k, are all the previous search directions. So we want the new search direction Pk plus 1 to be orthogonal to all these search directions. But here, if you look at this and compare it with Gram-Schmidt procedure, it will be exactly the same formula with one difference. What would that difference be? The notion of orthogonalization has been generalized. Okay, so it is orthogonal with respect to this weighting matrix A. That's what they call conjugate. These two vectors are conjugate, meaning not in the complex conjugate sense, but meaning that they are perpendicular to each other with respect to this inner product, Pi, comma, you can write this in several ways, ARI. Previously, we would have simply we would said that two vectors are orthogonal if Pi and Ai are, the inner product of that is 0. Okay, so here now it is with respect to this weighting function. So that's the generalization of this notion of two vectors that are orthogonal with respect to some weighting factors.
Could the A also be like a matrix representation of an operator? Say a linear operator?
A is a linear operator, right? In fact, if you look at the book by Ramakrishna and Amundsen, they would present A as an operator, a rule for multiplication that operates on some vector and produces some other vector. Okay, so the title of the book itself is called Linear Operator Theory in Chemical Engineering or something like that. It's from mathematics, but as applied to chemical engineering examples. There are a lot of chemical engineering examples there. Now, then they would say, if I have du equal to f, this symbolically it represents the same thing, but now u is a function, d is a differential operator, a rule. Okay, so if A is a matrix, d could be something like d squared dx squared plus 2d dx. So that's an operator part, but it operates on u. Okay, and the forcing function now is f. It could be 0, then you have a homogeneous system. If you have an external forcing on the function, then you'll have a non-zero thing. And so our task in this case for the linear system is to find that vector which when operated on A will give you the known vector. In this case, our task is to find that unknown function which when operated on D will give you the known function. Okay? And the problem really comes if you don't have this, but you have n u is equal to f. What is that? N is now a nonlinear operator. Okay, then you have nonlinear equations. It could be algebraic or differential. Okay, and we will very soon get into nonlinear algebraic equations and look at the dynamics of nonlinear systems. So that's what this step does. Okay, so this step simply allows you to calculate the next direction that you need to take in the iterative scheme. That is going to be based on your residuals. So the residual, the idea is that the residual contains components in all directions. Okay, and so initially it's going to contain in all directions, and you are going to successively explore directions that are still not explored in a dominant sense. So you subtract out all the components that you have searched previously, and then go in a direction that has a greater component in the unexplored direction. So this is going to be one key element of the conjugate gradient method, to find the new search direction. Okay. So once I found out my new search direction, I calculate the next guess. The next guess xk plus 1 is equal to the current guess xk plus, in the new search direction pk plus 1, a certain distance that I need to go. I still don't know what that distance is. I know the direction, but I don't know how far. I can just go a mile away and then still go far away from the solution. I don't want to do that, right? So how do I calculate this alpha k plus 1? once again using that inner product. It's basically finding the coefficient of this. Okay, so it is the inner product between pk plus 1 and b divided by the normalized length. Okay, and you can through algebraic manipulation that b is the same as r plus axk, xk, and how is that? And lastly, yeah. So b is the same as rk plus axk. How is that? It's simply axk minus b is equal to rk. That is, the residual at the kth step is the difference between axk, the guess at the kth level, minus b. So rearrange that, so b is the same as rk plus axk, and then pk plus 1 times axk is the inner product, which are complex, not complex conjugates, which are conjugate, which are orthogonal. Okay, so the second term in this one would be 0. So that gives us an estimate of how far, what is the best distance to go along this direction. So these are the three key steps in the conjugate gradient method. So you need to make an initial guess and then use these to successively find a new direction, a new guess vector. But in getting the new guess vector along the direction, we need to know, along this direction, we need to know how far to go. Okay, and that comes from this formula. So you put all these together and you get your resulting scheme. Okay, and it's written in a pseudocode. So the very first step is find some guess vector. Using that, calculate your residual, and let the residual search direction be the same as the residual. Okay, and then start your loop. Okay, so find the distance that you need to go along the direction, the initial direction that you have chosen, and update your new guess, new residual, and if the residual is sufficiently small, you've converged. Okay, so every time you calculate the residual, and if the residual is small, you've converged. If not, calculate a new search vector and go back and take a new step in that direction. Okay, so this is the repeat loop. And this is the place that you will come out of. If that condition is satisfied, then you will break out of that. And that should converge. Okay. Now the variations on these would be, instead of solving ax equal to b, there is something called preconditioned conjugate gradient. So you can, if the matrix is not well conditioned, for example. Now, do you know what a condition of a matrix is from linear algebra? If the determinant is very low, if it is scaled poorly, then all those factors, if it is not symmetric, for example, if it is not scaled, if there is one side of the matrix has large numbers, the other side doesn't have, for example, okay, then you need to do some balancing operations to enhance the convergence. Okay, so that would mean essentially instead of using A, you will use a modified version of A, but eventually you still have to show that you are satisfying AX equal to B. Okay, so there are a lot of variations like that that are built on this simple idea. And once again, the code, MATLAB code, is given. So just take that and run it. A question?
What happens if you don't make a good choice for X? Let's say we pick X that maybe doesn't have components in all the directions. Does the method blow up, or will it still find its way?
No. In the conjugate gradient, I don't think it would matter. Even if you pick a vector that does not contain in the eigenspace basis some of the components, because this doesn't make reference to any eigenvectors or eigenvalue analysis. It just looks at the direction of the residual vector, okay, and then scans the space and picks always new directions, so that you eventually, in a few iterations, span the entire space. And so the choice of initial guess will not have an impact on the rate of convergence, but it will have an impact on how many iterations you take, because the farther away you are from the final result, you need more iterations. But when I say rate of convergence, it is how you reduce the error per step, okay? And that will remain the same. But if the initial error is large, then you need more steps to get there. Okay, but I don't think, as long as, in fact, there are proofs, I think, for conjugate gradient method. If you have positive symmetric, positive definite matrix, then it is guaranteed to converge. But if it is not, then there is no guarantee. Okay? And theory is always, you need to limit your range of applicability. You cannot state a theory for solving all kinds of problems. So Wikipedia is a good source for all the variants of the conjugate gradient method. The most advanced in this one being something called GMRES, okay, generalized minimum residual method, which is a generalization of this for not just one vector at a time, but maybe spanning a subset of vectors and to accelerate the convergence. And all these algorithms have been implemented for efficient solving in different architectures, parallel machines, multi-cores, and stuff like that. So if you search the net, you will find freely available code written in C and Fortran that you can download. Okay, and most of the packages like Fluent and Consol, in fact, rely, the core set of numerical analysis codes were developed by LinPack, LabPack long time ago, and they are in the public domain. So people have taken that and implemented and improved, and those are the ones that are available in COMSOL. Even though COMSOL is a commercial code, you'll find pieces of code there that are taken from the public domain. So that, I think, completes my goal for linear algebra. The purpose is just to give you a review, a big picture of what are the methods that are available, what are the ideas that are used in developing those methods. It's not a comprehensive course on linear algebra alone, but that's a building block. So we want to move on to nonlinear systems very soon, but still we're going to look at dynamical systems now, ordinary differential equations. So we have been solving so far equations of the type Ax equal to b. That's for steady state length. Now I'm going to look at an equation of this type. In fact, I'm going to assume for the moment that there is no b. Okay, there is no forcing. Okay, but there is a transient term, an accumulation term. So dx dt equals ax, and I have a set of initial conditions given at t equal to 0, which is a vector x0. So x is a vector containing n components, and A is an n by n matrix. So I have actually a system of ordinary differential equations, linear equations. A is a constant. And again, in dynamical, if you take a course in electrical engineering, typically on linear systems theory, the whole course will be devoted to solving equations of this type. Now this is for constant coefficient. Then you will look at time dependent. So A could be a function of time, and still it is linear. Okay, and then you will have control theory basically. So you could have a B which could be a function of time. Okay, then you are trying to impose control on the system to take the trajectory of x as a function of t in a certain particular way. And then you get into controllability, observability, all those theories. We are not going to look at those. We're going to look at the eigenvalue problem, dynamical response of that, which is what our interest is. Okay. So how do we solve this particular problem? What do we mean by a solution to this particular problem? First, we mean that find that curve x as a function of t against t. Now I could plot a component of it, x1, x2, x3, etc. And starting from some initial condition, the trajectory may go something like this. So there may be a steady state. When there is a steady state, dx dt is equal to 0. So if you have no forcing, then x must be equal to 0. Okay? But you might have, for nonlinear problems in particular, a response where it just does this. There is no steady state. Or even for linear systems, we will see that under certain conditions, you might have a response like that, a periodic state, a sustained periodic state, or a steady state. Okay, that's what we mean. Find that curve which, when plugged into this differential equation, will satisfy the differential equation together with the initial condition that is passing through. So the way to solve that is to propose a solution. So the way that we typically solve differential equations would be the same. Okay, we have a set of toolboxes of functions. We take the function, plug it into the equation, and see whether it satisfies that. Okay, and when you have a new differential equation, you expand your toolbox. Okay, so you'll say, okay, now I'm going to define a new set of functions. These are all infinite series. Okay, so this may be Bessel function. If that is the equation, the infinite series that I get, I'm going to just label as Bessel function and put it in my toolbox. So when I get that differential equation, I know this is the solution to that. So in the simplest case, I'm going to propose a solution of this form. Now e to the power lambda t. What is e to the power lambda t? What is e? E is a?
Infinite series.
E is a number, natural number, just like pi. Do you remember what the definition for E is? It would be limit n going to infinity 1 plus 1 over n to the power n. Oops, power n. Something like this. Okay. So that turns out to be the number, what is it, 2.7, something like that, right? So if you go to MATLAB and type exp1, for example, it will give you what that number is. It's one of the natural numbers like pi, and there are a lot of numbers. But this e to the power lambda t is a special function built on that number. And it turns out that when you take its derivative, you're going to get lambda times e to the lambda t. It doesn't change. That's one function that doesn't change. If you take derivative of sine, it becomes cos, etc. But if you take the derivative of lambda e to the power lambda t, you will get lambda times e to the power lambda t. Okay, so that's what I'm showing on the left-hand side. Okay, so I'm going to let this vector x be equal to some unknown vector, because it has to be a vector on both sides. Okay, so I'm proposing a solution which says that x is going to be represented by some vector z, I don't know what that vector is, multiplied by e to the power lambda t, and then see whether I can satisfy that differential equation with that proposed solution. So take that and plug it into that. So on the right hand side, when you plug for x, z e to the power lambda t, you will get this. On the left hand side, take the derivative, okay, and then plug it in. So the derivative will be lambda times e to the power lambda t. And of course, z is there because x is equal to z times the derivative. Z is a constant vector. Okay, so the lambda t cancels out on both sides, and what I get is lambda times z is equal to a times z. It is again an eigenvalue problem. We introduced the eigenvalue problem when we were looking at the linear equations without really appealing to this idea, where it comes from. We just said, if you give me a, I'm going to define my eigenvalue problem as a z equals to lambda z. Okay, that is that vector which does not change when operated on a. Remember, a is an operator, so if I find that particular vector that does not change, then I would call that as an eigenvector, a special vector. Okay, but here you see another way of how to interpret that, where it comes from. So now it is exactly the same eigenvalue problem. So if you give me the matrix A, I should be able to calculate all these lambdas, and now I can give Z the interpretation that it is the eigenvector. When I started, I said it's some vector. Now I know it is the eigenvector. So if once I construct the eigenvalues and the eigenvectors, I can then know the solution, because I know Z, I can put it back, I know the eigenvalue lambda, so I know what the solution is. Now if you have an n by n system, I will have n eigenvalues and n eigenvectors. Every one of them will satisfy this equation, right? So linearity allows you to superpose. So addition of all of them will also satisfy the differential equation. Okay, so you need to weight these n solutions in such a way that you satisfy your initial condition. Okay, and that's the basic procedure. So if x1 and x2 are, these are, again, I took this from Wikipedia. So these are stated as facts. If I have two solutions, x1 and x2, that satisfy the differential equation, a linear combination of them will also satisfy that differential equation. And if you have A as an n by n matrix, then there will be n eigenvectors and n eigenvalues. So your solution would be a linear combination of all of them. Okay, and this we already saw. If you get all these eigenvectors, arrange them in column, packed to form a matrix, and the determinant of that matrix will be, should be non-zero. They are linearly independent. Okay, the test for linear independence is, sometimes this matrix is called the Wronskian W. The same idea applies even when you go for functions. If you have n linearly independent functions, you form the Wronskian of those functions, and that must not be zero. The determinant of that matrix should not be zero. Then you have established that those are linearly independent vectors, so your solution can be constructed as a linear combination of those. But the only difference between this and what we saw earlier is every one of them is a function of time. These vectors are not constants, but they're functions of time, and they will satisfy that linear ordinary differential equation. Any questions? Let's see. Any questions from those online? Not at the moment. Okay. Good. Let me go back to the. Okay, good. Thank you. Okay, so the solution is represented as a linear combination, summation of all those solutions, but alpha I is the unknown factor, weighting factor, which I must determine by using the initial conditions. Okay, so evaluate this at t equal to 0, put t equal to 0 here, so e to the power 0 is 1, and all you will get is alpha I, so this will become x0, x at t0 is equal to summation of alpha I zi. Okay, and x0 is a vector and zi are all vectors. Alpha I is the unknown coefficient that I need to find out. So I'm going to use once again the orthogonality of these vectors. Okay, A is symmetric and so zi are orthogonal. So take the dot product of this on the left side and right side with zj. So this is the dot product, x naught times zj. And in the summation, zj dot zi will be equal to 0 because they are all perpendicular to each other. So only when I equal to j, you will get a non-zero one. Okay, so you can calculate. So all the highlighted ones are known. So you can calculate what alpha j is. Because in that equation, the initial condition is given, and you know each one of these eigenvectors. You have to calculate the eigenvectors to solve this problem as well. Okay. And this is where we are forced to calculate the eigenvalues. For solving the algebraic equations, we really don't need the eigenvalues and eigenvectors. It gives us a nice interpretation for understanding it, but the most efficient way of solving Ax equal to B is either LU decomposition or conjugate gradient type of methods. But for solving a linear ordinary differential equation, you must find all the eigenvalues and the eigenvectors. Okay. Is that true? You might say, you might challenge me by saying that if I give you an equation, say d square x dt square plus 2 dx dt plus 3x equal to 4. Do I need to calculate the eigenvalues of those to find the solution? What do you normally do in a differential equations course? You just write the characteristic equation, right? Immediately the characteristic equation would be lambda squared plus 2 lambda plus 3 equal to 0 for the homogeneous equation. But what are those? Those are the eigenvalues. Okay? Because it's a 2 by 2 system, you can do it by hand. But if you have a 100th order equation, that is equivalent to 100 first order equations. And you will have to find all the characteristic roots of that particular problem. Okay? And pretty soon you will see the connection between this and the representation that I have in vector matrix form, dx dt equals ax. They are equivalent. You can convert one to the other. Okay. Any questions? This material is from an ebook that I downloaded, and I guess probably I should put it on, or we'll put the link on the Moodle page for this. It's a very nice book, undergraduate level, on differential equations. The whole book is devoted to differential equations. So he does review the eigenvalues, eigenvectors. But what I wanted to talk about in this is to prepare you for this notion of a phase portrait plot. Okay, what do you mean by that? So it is essentially a plot of state, one state against the other. Okay. So if I have two equations, as in this case, okay, x1 prime equals x1 plus 2x2, x2 prime equals 3x1 plus 2x2. So in matrix notation, you can write this as the prime here denotes derivative, not transpose. Okay. So the x prime means that it's a vector, dx1 dt, dx2 dt, and this is a vector of the unknown that we want to solve. Okay, so here you are given a 2 by 2 system for which it's very easy to write down the solution. And what we want to focus on is how does the response of such a system look? When I plot, I can plot two kinds of graphs. One is x1 versus t. That is what we will call the time series. The other one is x1 against x2. That is what is called a phase plane or a state space representation. So here on such a curve, t would be parametrized. So for example, initial condition is given. Okay, in this particular problem, is it given? Let me see. I guess he has not given that to you. But suppose the initial condition is given as x naught is equal to 1, 1. Then my initial point will be somewhere there. And then as I integrate in time, I will get a curve like that. And that may be the final point. So this may be the initial point, that may be the final point. And that curve is called the state space trajectory. Okay? And we are interested in understanding what type of responses are possible for the linear system, because when we go into nonlinear system, the same kinds of responses are possible near an equilibrium point, because we will linearize the equation. Nonlinear systems are very difficult to solve. The way that we are going to solve is linearize it locally and then follow the trajectory. Okay, so in this particular case, it's fairly easy to solve. So I'm going to go through it quickly, but I want you to, if you have not seen this, go through the steps that he has given in detail. The first thing he's going to illustrate is how can one construct the phase plane portrait. So what you do is, in such a plot, x1 against x2, pick a range of points, for example, -1, 1, and plug that in and calculate what is x prime is, the derivative at that point. Okay, follow this one carefully. Okay, I have x1, x2, and I pick a point. In this particular case, I have picked x1 is equal to -1 and x2 equal to 1, a point here. And at that point, I calculate the derivative by simply plugging into the equation. So the derivative is 1 minus 1. What does that mean? Which direction is the derivative pointing to? It's pointing in the positive x1 direction and the negative. So it's pointing somewhere here. Okay, so I'm going to put that arrow. Then I take another point, 2, 0. And I plug in the value and I get the derivative for that. So 2, 0 is going to be somewhere on this axis. X is equal to 2, y is equal to 0, that point. Okay, and then plot the vector. Where does that vector point out? It is 2 units to the right and 6 units to the top. So that vector may be pointing out something like this. So you take a dot of points everywhere, and at each point calculate the vector and plot it. What does that give you? What do you think it will give you? We are not solving any differential equation. All we are doing is picking a random set of points, and each point I'm plotting the vector of which direction x1 prime and x2 prime are pointing to in that space. And this is what you will get. The graph that you see on the left. Okay? So these are all various points, and at every point we have plotted the direction of the vector. So you can do that very easily in MATLAB. what this tells you is the flow of the trajectory in that state space. Suppose I give you that the initial condition is somewhere here, and I say go and plot the solution trajectory. What will it look like? All you need to do is everywhere follow that, right? Because the trajectory is going to be tangent to that vector everywhere. Okay, so you can easily construct the trajectory. So if I have an initial condition here, it will lead to a trajectory like that. If I have an initial condition here, it may lead to a trajectory like that. Okay, and that's what he's plotting. Okay, these are the trajectories. So it doesn't tell you a very particular solution for a particular initial condition, okay, but it gives you a complete map. So wherever the initial condition you place, from there I can approximately get an idea of which way it is going to go. Does it tell me how fast? No, remember, at every point on such a curve will have a certain time value. So I can say the time starts for me at this point, t equal to 0, I'm here. And if I ask you to say, what is the time when I reach that point, will you be able to do that? Not from this graph, right? Because this graph is parameterized. Unless you put tick marks there for every second or something like this, you will not be able to tell how long it took for you to reach from some initial starting point to some terminal point. Okay? In order to do that, you need to plot the time series plot, which would be the x1 versus time and x2 versus time. Okay. The other thing to notice is there are two unique directions in this, right? One is this one. The other one is somewhere here. And he highlights this in purple here. Okay. What do you think those directions could be? The steady state. The steady state, what would the steady state be in this particular problem? When x dot is equal to 0, this matrix determinant is not 0, the steady state must be 0 at the origin. Okay. So are we going to go to the steady state if we start from any initial condition? That's one of the questions that we want to understand. That relates to stability and dynamics, right? So in this particular case, no matter where I start from, I always seem to go in those directions. Okay? I seem to be attracted towards this direction, but eventually diverge away from that direction. Okay? So the steady state is right at the origin. So we will conclude that the steady state is not stable. You will never reach that steady state. It's an unstable steady state. Okay? It turns out that those purple lines are the eigenvectors. Okay? So there is one stable eigenvector, meaning this is a 2 by 2 problem. So if you calculate the eigenvalues, you will get one negative eigenvalue, one positive eigenvalue, and the solution is given as e to the power lambda 1t and e to the power lambda 2t. So if you have a positive eigenvalue, that will cause it to diverge, go away from the origin. Okay? So if these are two eigenvectors, the purple ones, which one will correspond to the unstable one? Suppose I label this as lambda 1 and I label this as lambda 2. These are the two eigenvectors corresponding to those two eigenvalues, right? So lambda 2 must have a positive real part so that it blows away. Okay? And lambda 1 has a negative real part, so initially it attracts. Okay, any questions on those? These are the dynamic response for this particular problem. Okay. So we're going to look at a number of examples taken from this book to understand various types of responses that are possible. So all are the same format. It's a 2 by 2 ordinary differential equation, linear coefficients, constant coefficients. The only thing is these numbers are going to change in each one of those examples. And here we have a particular initial condition that we need to satisfy. Okay? The procedure is find the eigenvalues and eigenvectors. Okay? So here I write this eigenvalue matrix, and what is the characteristic equation for this? Just that. Okay. As I said, this is equivalent to a second order system. So a second order system can be converted to a system of first order, or first order can be converted into second order. How would you convert that? Just eliminate one of the variable, right? So take the derivative, for example, from the first. This is essentially like Gaussian elimination. Take the derivative from the first equation and eliminate x2 and get an equation in terms of x1. But when you take the derivative, you will get to the higher order. Okay? Because you, for example, in the second equation, you will have dx1 dt plus dx2 dt, but you want to get rid of the dx2 dt. So from the first equation, take the derivative and replace it. So using the same idea as Gaussian elimination, eliminate one of the variables, and you can get an equivalent second order system. Write its characteristic root, you will get exactly this. Okay? And in this particular case, solve this. You can do that by factorization, and you will find that these are the two roots. So immediately you can conclude that the system is unstable because you have a positive eigenvalue. So even if you have 100 equations or 1,000 equations, if there is one eigenvalue that is positive, your entire system is unstable. Okay? So going back to the previous curve, you can argue, and this is the thing that we talked about, if I choose my initial condition to be exactly on this eigenvector, what would happen then? That initial condition does not have a component in the second eigenvector direction. What should happen then? What does it mean in terms of the solution? The solution x of t is going to be written as c1 z1 e to the power lambda 1 t. z1 is the first eigenvector plus c2 z2 e to the power lambda 2t. Right? So if I pick my initial, the c1 and c2 are determined from what? The initial condition, right? So if I pick my initial condition in such a way that C2 is 0, then I'm enforcing that my solution is entirely in the subspace. The subspace in this case is just a line, right? Then I should get a stable response. That part of the thing is stable response. So if I pick my initial condition to lie on that eigenvector, then it will go to the origin. Okay? But in reality, you always have perturbations on the system. Okay, so the slightest perturbation will cause it to develop a component, and the moment it strays away into that space, away from that line, it's going to pick up that component and it will become unstable. Yeah.
In reality, you'll have the perturbations, so you can't start on that initial point, that exact initial point. Mathematically, though, if you're trying to find this round-off error or any other errors like that, you'll still find the steady state, won't you? Because you're actually...
That's a very good question. And when we were working on hydrodynamic stability problems, this was about 10 years ago, there was a lot of discussion about this. The question is, if there is an unstable state in a fluid mechanics problem, okay, can you reach that state by using this time integration of a dynamical system? And the answer turns out to be no, because in physical systems you can never observe that unstable state because there are always random perturbations in the pumps, vibrations, or whatever. In computers, the random perturbations come from round-off errors. Okay, so you will never be able to get to those unsteady states. You can calculate those unsteady states, and those algorithms of continuation scheme that Ronald will illustrate and I will talk about were developed in the late 70s, 80s, or something like that. So, but we knew beforehand from this kind of a simple analysis that there are unstable states. When there are stable states, there are also unstable states to a nonlinear equation. The problem is even now, if you're given a nonlinear equation and asked to predict a priori how many solutions will this equation have, the answer is no. We don't know. There is no theory that will allow you to tell how many solutions there are. Okay? So there is a wonderful paper by Brooke Benjamin in Journal of Fluid Mechanics called bifurcation theory. And there he lays out, using topological theories, that how you can detect unstable solutions. There are some indices that he counts that must remain invariant. So based on that, and he did some beautiful experiments on the Taylor-Kuhn flow, and it was a very interesting sequence for me. So that paper was published, and he found out 21 different steady-state solutions for a particular problem. On the same operating condition, you have different number of cells that you would observe in that. And if anybody wants to take that as a project, it's a nice project to explore. Okay? And he gave that as a challenge to numerical analysts at the time, that it is very difficult. The numerical techniques have not advanced to the stage that we can calculate all these stable steady states. And then using his theory, he says that there is also unstable states. So there are a total of maybe of the order of 40 steady solutions. A lot of them are unstable, but here are the stable solutions that we have experimentally observed. And CFD was just taking up shape at that time. I'm talking about the 80s, mid 80s, I think. But within a year, somebody from Australia actually computed all those solutions by solving Navier-Stokes equation. The secret is hidden in the Navier-Stokes equation. So he was able to compute all the steady-state solutions, but using these iterative methods. That's another important point. Iterative methods mimic the same behavior as dynamical systems. Okay, so if a dynamical system is unstable, the iterative method is also not going to go to that unstable steady state. So the short answer is, if it is unstable, any iterative method or dynamical integration method will not lead you to that unstable state, even if you pick your initial conditions very carefully to remain only within the stable manifold. So you call this, like, this is for a 2 by 2 problem. So there is one stable manifold, one unstable manifold. Think of this as a partial differential equations are continuous systems, right? But even if you discretize them and you get 100,000 equations, all you need is one unstable eigen value. And you cannot live only in the stable subspace of that. The round-off error will force you into that. Okay, any other questions or comments? How about there? Okay. Okay, now you need to find the eigenvector. So this is really a very nice book on differential equations because he brings out everything. He doesn't teach the way I do. I just give you the overall picture, but he works through every step. Okay, that is the differential equation. These are the eigenvalues. Then how do I find the eigenvectors? Well, I take that eigenvalue and put it back in there, and now I have this matrix where lambda 1 and lambda 2 are the two components of the eigenvector corresponding to this eigenvalue that I'm solving. Okay, and what would happen to the system? What do you know about this system? It's singular, right? We found that value of lambda 1 by setting that equal to 0, determinant of that equal to 0. Okay, so what does that tell you? That there are infinitely many solutions for this problem, right? So you need to pick lambda 1 arbitrarily, and then you can calculate what lambda 2 is. Okay, so he simplifies this equation. That's a relationship between the two components of the vector, and then you pick one of them arbitrarily. So here, okay, so you pick lambda 2 to be equal to 1 arbitrarily, and then you have the direction of the first eigenvector, minus 1, 1. Okay, and then you take the second eigenvalue, go through the same process, and pick arbitrarily one component of that, and that gives you the second eigenvector. Okay, so I have the two eigenvectors. I can plot it on that state space. And here is the solution. And C1 and C2 are the two constants that I need to find. Okay, and I find them by evaluating it at t equal to 0. Put 0 there. That's your initial condition. So that vector is known, and these are the eigenvectors that I know. Solve for C1 and C2. Okay, and that gives you the complete solution. And then you can plot that particular solution passing through that initial condition on that state space. Okay, so how does that look like? Here it is. These are the two eigenvectors that you see here. Okay, eigenvector 1, eigenvector 2. And you can point the direction of this because the first eigenvector is negative, the second one is positive. So this is an attractor. If you start on that, initial condition starts on that, it will be attractive, and this is a repeller. That's one of the simplest dynamical responses that you can have. Of course, if both are negative, then both are attractors, then you have a stable steady state. But this would be an unstable steady state. And you can plot the trajectory of that, and the trajectories will look like this. Okay? And it's only one of those trajectories that we have calculated there, starting from some initial condition. And it's called, this equilibrium solution is called a saddle point, and it is unstable. And this is kind of repeated for a number of examples, each one giving rise to a different response. So this is another example. The only difference is the choice of this matrix. These are different set of numbers and a different initial condition. The process is the same. Solve for the eigenvalues. Okay, and what do you find here right away? Both are negative. So it is a stable equilibrium. Okay, and for each eigenvalue, you calculate what the eigenvectors are. Okay, so in this case, the eigenvector is 1, 4. And the second eigenvector corresponding to this is minus 1, 1. Okay, and you can map that. So in this case, well, I guess still trying to find a steady state solution for a particular initial condition. Okay, that means find C1 and C2. And so C1 is 3 over 5 and C2 is minus 2 over 5. Those are the initial constants determined by the initial condition. But the dynamics is determined by e to the power minus part, e to the power minus t and e to the power minus 6t. In such a cases, the lambdas are also interpreted as time constants for the particular problem. Okay, so here there are two solutions. We will call the second solution as a fast solution and the first solution as a slow solution. Why is that? For the same amount of time that you travel, this will change much more faster. Okay, so the lambda is a measure of the time constant, how fast a particular component is changing. Okay. So here sketch is portrayed for that particular problem, and so you're plotting the eigenvalues, the eigenvectors here, and putting the direction for them. Okay, so lambda 1 and lambda 2. You know how to plot these, right? You have the components. So if you go back to the components for lambda 1, it is 1, 4. The other one is 1 minus 1, 1. Okay, so 1, 4 would be go 1 unit in here and go 4 units up, pick another point, and then connect those. Okay, and minus 1, 1, you go minus 1 here and then 1 there. No, sorry, upwards. Otherwise, I'll get the same again. So minus 1, 1. So you go there and connect those. Okay. Now, this idea is beautifully illustrated with chemical engineering examples in an article by Wei and Prater in Advances in Chemical Engineering. This appeared in '62. It's a very long article, 130 pages or so. And the application that he talks about is chemical reactions. If I have, for example, 3 components, species A1, A2, and A3. A1 can go to A2, A2 can go to A1, A1 can go to A3, A3 can go to A1, etc. And there is a rate constant for each one of them. So So this will be K32, K23, etc. So he treats these each one as a concentration. So in a batch reactor, if you put all these three species and they are interacting with each other, you can get three ordinary differential equations to track the concentration of each one of these species. And you get, if they are all first order equations, first order chemical reaction, then you'll get three ordinary differential equations that are linear. And all these ideas of eigenvalues, eigenvectors can be interpreted in terms of reaction paths. Okay, so in that particular case, if I have a trajectory, so these would be the eigenvalues in that space, and x1, x2 will be c1, c2, the concentrations, right? So if you have initial concentration, something like this, you can look at the trajectory. Will it go like this, or will it go like this? So in this particular case, let me ask you to speculate. Which way would the trajectory go? If I start from some neighborhood here, okay, and given that I know the lambda 1 and lambda 2, let me just write that down. What was lambda 1? Lambda 1 was -1 and -6. So here lambda 1 was -1 and lambda 2 was -6. Okay, so which way, right, can you speculate which way it will go? How would you determine that? Right, it should basically, all the trajectories will go something like this. Okay, because the slow component is the first component, lambda 2 is the fast component, right? So he then goes on to see how I would actually take these samples of concentrations. The idea is to calculate or determine from experimental concentration measurements the best value for the rate constants. Okay, how do you calculate rate constants from reaction engineering? Do you know? You just measure concentration versus time and plot one against the other and match it with a model and back calculate the reaction rate constant. So this one will allow you to reduce the errors because you can do the experiment repeatedly for different concentrations and then actually calculate what is the eigenvalue, the vector that corresponds to that. And then in an experiment you can actually pick an initial condition that does not have any component. Still there will be errors that will control introduce, but he talks about the whole 130 pages is about what are the sources of errors and how you control it. And it's a beautiful illustration of linear eigenvalue problem to a very practical chemical engineering application. When I was a graduate student, I read that article fully, so I would encourage you to do the same thing. Okay? Yeah.
In that example,
Yeah.
chemicals or the concentrations, because you're restricted to positive values for concentration,
Yes.
does that mean there also has to be an eigenvector along the x-axis?
Well, a very good observation, but you need to read the full paper to understand the full story. There is an equilibrium point, right? And the concentrations have to live in a positive space. So he constructs a ternary diagram to represent these concentrations.
Right.
And the equilibrium point will be corresponding to the zero. Turns out to be a zero eigenvector, null eigenvector. Okay, so the equilibrium position corresponds to that, and then all the other So in a ternary diagram, you can plot two other eigenvectors in there. Okay, but you are right. You are, from a practical point of view, you are forced to live in that quadrant of the concentration space. Yeah. Oh, that's what you guys speculated. The trajectory should be going parallel to lambda 1 because the other one is a fast one. So the lambda 2 component will decay fast. That's what this says. Okay. So the lambda 2 component are going to be parallel to this, and lambda 1 components are going to be parallel to that. So the lambda 2 components decay very fast, and then only the lambda 1 component is left in your solution, and that will decay towards zero. Okay? So all the trajectories should be kind of tangent as it approaches the equilibrium point to lambda 1. Yeah, equivalence between a second order system, we talked about this earlier. So if you give me a second order equation, again with two initial conditions, I can represent that as an equivalent first order system. How do I do that? I just introduce new variables. Okay. So I say x1 is equal to y. Y is the variable that is given that I need to find. But I'm going to let x1 be equal to y. And then I'm going to define a new variable x2 as simply y prime, the derivative of y. Okay. Then I take the derivative of this equation. So x1 prime is equal to y prime, but y prime is defined as equal to x2. Right? So this gives me the first equation. All I've done is I've taken the derivative of the first equation, x1 prime equal to y prime, but y prime is defined as equal to x2 from the second equation. So my equation is x1 prime equal to x2. Okay? And then the second equation is x2 prime. If I take the derivative of the next equation, x2 prime, I'll get y double prime. But y double prime I get from this, because this is the equation really I want to solve. So it is only in this tab I'm extracting the information from the equation. I move these to the right hand side. And then I replace y with x1 and y prime with x2, because that is my definition here. Okay? So it is going to be minus 3 over 2y minus 5 over 2y prime. And then I replace that in terms of x1 and x2. So I have the equivalent representation as a system of first order equation. This you can do even for 3x3 system, 4x4 system, etc. Just have to define additional variables. If I had a third order equation, I will define x3 equals y double prime. Okay? So you get this equation, which is the matrix representation of this equation. And then you have the initial condition. So y is the same as x1, so x1 is minus 4. Okay, and x2 is same as y prime, but y prime is 9. So x2 is 9. So that gives you the initial condition. So you can solve using the same idea. So this is your characteristic equation that you see here. If you had written the characteristic equation directly without going through this route, you would have gotten the same equation from there. Okay? Now find the eigenvalues. So what do you say? Is this system going to be stable or unstable? Unstable. Oops. Because you have, what is happening? You have an unstable node there. Okay? So it's the same procedure. You find the eigenvectors for each one of them. Let me just go through those quickly. That's the first eigenvector, and here is the second eigenvector corresponding to the unstable node. And the particular solution for the initial condition, same idea. So you should really go through this if you want to understand all the details, but it's essentially a repetition of the same process. As I said, it's from an undergraduate course, I think. So that shows essentially the equivalence between a higher dimensional system and an equivalent first order system. This one is a different example that shows the case of complex eigenvalues. So far our examples have resulted in simple eigenvalues. So they are positive or negative. That gives to either a saddle node or a stable equilibrium point. Now if I take just a different set of coefficients, okay, they go through the same process, and I get into this situation. What is the situation here? The characteristic root is lambda square plus 27 equal to 0. So lambda is equal to plus or minus 3 square root of 3i. This is a purely imaginary eigenvalue. There is no real part. So the next case would be one where you have both real part and imaginary part. Okay? But let's see what happens when you have a purely imaginary part to the solution. Maybe you can guess. What would that be? If I have purely imaginary eigenvalues in the state space, how do you think the concentration, the states will look? Can you plot eigenvector in a state space? State space contains x1 and x2, the real numbers, right? I have a complex pair of eigenvalues, plus and then minus 3 square root of 3. So if I find the eigenvector for that, that means I'm going to substitute the eigenvalue and solve for the eigenvector. So what happens to the eigenvectors? This is the relationship between lambda 1 and eta 1 and eta 2, the two components of the first eigenvector, that is complex, right? And so if you go down, you'll find the first eigenvector is a complex eigenvector. Again, the same idea. You have some degree of freedom, so you choose one of the components arbitrary, but still you'll end up with a complex eigenvector. And these must occur in complex conjugate pairs. Okay, so if you try to find the second eigenvector, it will be that, and you can write the solution in terms of that eigenvalue and eigenvector. But you know the Euler's formula, e to the power I t is cos t plus I sin t, right? We've seen that in fluid course too, right? So you use that and express the solution in this form. And so the response in the state space is going to be involving sines and cosines t, right? That will be a closed loop, okay? So the plot, this is just getting the complete solution detail, but let me just go to the plot. Sketch the phase portrait for this particular case. There it is. Okay. So in the nonlinear case, these are called limit cycles, a closed response. But for the linear system, these are just circles or whatever you want to call them. So what are the possible responses that we have seen so far? An unstable node with one unstable eigenvalue and the eigenvector, asymptotically stable. Okay, all eigenvalues are negative. This we have not explicitly seen, but so I want you to kind of speculate what is happening here. It's called an improper unstable node and an improper asymptotically stable node. What do you think is happening here? It's coming from a 2x2 system.
Slow mode is unstable. Like it tries to come to the solution, but then the slow mode diverges.
No, all of them diverge, right? Even if you start anywhere close to this, it's going to diverge.
So what are the eigenvalues of zero?
It's just
A degenerate case. Okay, so it could be two eigenvalues occurring at a multiplicity of 2, and both are unstable in this case, and both are stable in this case. Okay? So wherever you start, you reach that particular thing. So the point, I think, is that the eigenvalue analysis is so important in understanding the dynamical response of such systems. A saddle node that we have seen and a center that we have seen. These are the complex eigenvalues that give rise to it. So what do you think is happening here? A spiral unstable, a spiral asymptotically stable. We haven't seen an example of this in the 2x2 examples. But can you speculate by knowing so far what possible eigenvalues could be? They could be real, positive or negative. They could be purely imaginary. The only thing that we haven't examined is they could be complex that will involve a real part and an imaginary part. So the imaginary part will give rise to a cyclical behavior. A real part will give rise to either a growth or a decay. So if the real part is negative, then you will get a decay that basically goes towards the center. Okay? If the real part is positive, then even if you start very close to it, it's just going to have an unstable. So it is a real part of the eigenvalue that determines the stability. The imaginary part determines the character of the evolution. And if you have a purely imaginary part in the nonlinear systems, that gives rise to the starting off of dynamical response. I think that's probably all I had for today. So we finished a little bit early. Okay, let me see. Are there any questions from the guys? You're all still there, listening. Okay. So I think in the next class we will start looking at nonlinear dynamical systems. Okay. Again, I want to go through solving nonlinear algebraic equations and nonlinear ordinary differential equations using numerical methods, but interpreting it using these concepts of what happens at an equilibrium point, stable or unstable, is important. That's why I went through this in some detail. So we don't have classes for the next week, and the week after Mrinal will take. So I guess you won't see me for 2 weeks, and then I will come back and continue with the nonlinear algebraic equations followed by ODEs, and then we'll move on to functional approximations. Okay, but I will put the projects as soon as I can early next week, and then by email we can continue to correspond, and you guys pick the projects, and then we can start working on it. And after the end of next week, I'll post the second assignment that will involve what I guess Mrinal is going to do using COMSOL, how to solve, or using MATLAB, both of them, how to solve nonlinear algebraic equations. Okay, if there are no questions, I guess we will call it quits for the day. All right.